So in this lab, we are going to do synthesis and titration of a copper salt. We're going to make a compound between copper and ammonia and then titrate it with HCl to determine how much ammonia was in the compound. So let's start with some background information. Anytime you dissolve up a copper salt in water, it's going to form the hexamine ion, which is pale blue in color. It looks like this. Okay, the solution that you're going to make in the lab initially looks something like this. So when you add 15 molar ammonia, you begin a series of equilibrium steps. I mean, ultimately the compound that we're going to produce is the tetramine, but that doesn't happen all in one step. So there's a series of steps, and each step is an equilibrium. So in the first step, the hexamine reacts with an ammonia, all right, and one of the ammonias kicks out a water and forms this compound. The second step, another ammonia goes in, kicks out a second water, and so on until we get down to the last step where you form the tetramine. So in the synthesis of this compound, we're going to use a high concentration of ammonia to drive these reactions to the right. If you remember Le Chatelier's principle from general chemistry, if you want to drive a reaction to the right, you jack up the concentration. You make the concentration higher. We're using 15 molar ammonia, which is very high compared to what the concentration of your copper ion is in solution. So we're going to drive the reaction to the right, but it stops with the tetramine. Copper likes to hang on to two of those water molecules. The replacement of the fifth and sixth water molecules would only take place in liquid ammonia. That is liquefied ammonia, not ammonia dissolved up in water. So the ammonia concentration would have to be higher than what we can get it in aqueous solution. So ultimately the compound that's produced is the tetramine. So that's the purpose of this experiment. What compound is really being produced here? Are we really getting what we think we're getting? Perhaps we're getting the tetramine without the two water molecules. Or perhaps we're getting the compound we think. Or perhaps we're getting a pentamine or maybe even a hexamine. So how are we going to tell the difference between these two? We're going to titrate them to get the ammonia content, but what is going to be reported? What is going to be reported is the mass percent of ammonia in the compound. So how would you calculate that? It's the mass of ammonia in the compound divided by the total mass of the compound times 100 to convert it into a percent. So let's say in this last example that you wanted to calculate, and this is one of your pre-lab questions, is to calculate the mass percent of ammonia in these compounds. How would we do this last one, for example? Then we would take the mass of 6 ammonia molecules, that's the mass of NH3, divided by the total mass of the compound. What's the total mass of the compound? The mass of the copper plus the mass of 6 ammonia molecules plus the mass of a sulfate. So the mass of ammonia divided by the total mass times 100 to convert it into a percent. And before you get confused and ask, okay, where are these sulfates coming from? The starting reagent in this synthesis is copper sulfate pentahydrate. So the sulfates are still there, and we isolate the compound. In the procedure, it precipitates out as the sulfate salt. But each of the above compounds has a different mass percent of ammonia. Maybe not hugely different, but different nonetheless. So how will the how will this be determined? How are we going to figure out how much ammonia is in the compound that we make by titration? We're going to titrate with 1 molar HCl. Okay, so what does the HCl do? The HCl protonates the ammonia and converts it into ammonium ion. Now, ammonium ion cannot be a ligand. It does not have an unshared electron pair on it. Ammonia has an unshared electron pair. Ammonium does not. So what happens is you dissolve the compound. After you make the compound, you dissolve it up in water. It begins to equilibrate, and the ammonia molecules, if they come off the copper, they protonate, okay, and that converts it into ammonium ion, and ammonium ion can't be a ligand. As the ammonias get pulled off, they are replaced with water because it's dissolved up in aqueous solution. There's lots of water floating around. So basically, the end product is the hexamine. So basically, we're back to a diluted version of greatly diluted version of what we started with. But it's a 1-to-1 stoichiometry, meaning that 1 HCl reacts with 1 ammonia. So once you figure out how many moles of HCl you've added, it's the same as the moles of ammonia in the sample. How do you figure out how many moles of acid you've added? It's the volume times the concentration, right? And make calculations easy. The molarity is 1 mole per liter. Just be aware you'll have to convert the volume from milliliters into liters. So you'll go from moles of HCl to moles of ammonia, and then multiply that by the formula weight of NH3 to convert it into a mass, and then you're going to divide it by the mass of the sample that you titrate to convert it into a mass percent of ammonia. So what is the procedure for the first week? We're going to do this over 2 weeks in the lab. The first is the synthesis of the compound, and the second is the titration. So you're going to weigh out 7 grams of copper sulfate pentahydrate. You're going to add it to a 125 ml flask, dissolve it up in 15 mils of water, and you're going to have to heat it to dissolve it. Okay, and it looks like this. I did it here on a half scale, so this was basically 3.5 grams in 7.5 mils of water, but the concentration is the same. This is what it should look like in the lab. Okay, a light blue colored solution. So you're going to start adding 15 molar ammonia, a few mils at a time, and you're going to go through a whole series of color changes here. Okay, the first thing you'll see is it's going to change to more of a turquoise colored. Okay, that is the production of copper hydroxide. Okay, so that's going to look like this. The color is definitely different. You can see that there's a precipitate in there. Okay, so the color is going to change from this pale blue and completely soluble to this turquoise color that's a precipitate. One more time. Okay, that's copper hydroxide. Then you start keep adding ammonia. What's going to happen is we get the ammonia concentration high enough, this redissolves, and it starts turning dark blue, right? And you wind up with a solution that looks like this. Now notice this is no longer cloudy. You could, except for the dark color, you can almost read through this. This is transparent. There's no precipitate here. Okay, so you're going to add ammonia until the solution is transparent. Okay, remember, now there's a difference between colorless and transparent. All transparent means is that you can see through it. So then we're going to add 15 mils of ethanol. Okay, so what's that going to do? Ethanol mixes with water, but it's less polar than water. So ultimately, adding the ethanol reduces the solubility, and causes the compound to precipitate out. Okay, and after you add the ethanol, you'll see something like this. You can see there's a solid in there. Okay, there's some solid in the bottom, so you definitely got some solid in there. And now the color is still that deep blue. Okay, so last you're going to suction filter the solid, right? So one more time, we started out, we dissolve it up in water, it's pale blue. You start adding ammonia, it'll change this turquoise color, you'll get a precipitate of copper hydroxide. Keep adding ammonia, and your precipitate redissolves, and you get this dark blue transparent solution, right? Then you add the ethanol. That will cause it to reduces the solubility, causes the compound to precipitate out, and you suction filter it to recover the solid. And ultimately your solid looks like this after you suction filter it off. Let's compare the color to the copper sulfate starting material that we started with. The copper sulfate pentahydrate looks like this. This is the compound that we're making. If you want to see the two side by side. Okay? So, what's our procedure for week 2? You're going to obtain, now this is where we're going to do the titration, you're going to obtain 325 ml Erlenmeyer flask. You're going to add between 1 and 1.5 grams of the compound to each flask. You want to record the exact mass to every digit the balance gives you, 3 places past the decimal. You can use any mass between 1 and 1.5, but you have to record the exact mass. So, 1 for the 1.00 for the first, 1.25 for the second, 1.50 for the third, doesn't really matter as long as you record the exact mass. And it's a good idea to use a different mass for each titration. So when you dissolve it up, the solution's going to turn cloudy because all those equilibrium reactions now start happening in reverse. And there's no longer the huge excess of ammonia to drive it to the right. So it's going to look cloudy. You're going to want to add the HCl. You're going to titrate with the hydrochloric acid until there is no trace of cloudiness. Alright, so until it becomes transparent, you can see through it, it doesn't look cloudy any longer. Now, this is not going to be an exact titration. It's not going to be like an acid-base titration with phenolphthalein where one drop is going to make the difference between 2 extreme color changes. So you'll have to use some judgment as to when exactly to stop the titration. So last, I want to say something about working with burettes. I think titrations are important. We're doing 3 of them over the course of the lab. So first of all, a burette, right? You've probably worked with these before. It's this big, long, skinny tube that starts at 0 at the top and goes all the way down, right, all the way down to 50 at the bottom. It holds 50 mils, okay? So, another thing here about a burette is this thing at the bottom here where you open and close during titration. That's called the stopcock, alright? So the stopcock is open when it's parallel to the tube and closed when it's perpendicular, right? So that's open, and that's closed, right? So when you start to fill up your burette, you want to be sure it's in the closed position, right? That needs to be closed. One more time, parallel is open, perpendicular is closed. Now, in a burette, or any glassware, water forms a curved surface called a meniscus. It looks like this. It's going to form a curved surface called a meniscus. You always want to read the bottom of the meniscus, not the top, not the middle. You read the bottom of the meniscus, right? So you always read the bottom of the meniscus, okay? Now, this is important in that every burette volume should be recorded to 2 places past the decimal. You read to the tenths and you estimate to the hundredths. So let's go back and look at our picture of our burette here. Alright, let's say this is 11 and this is 12, right? So that would make this 11.1, 11.2, 11.3, and 11.4. That can be read directly off the burette. So we're past 11.3, but we're not quite to 11.4 yet. So you can read the tenths directly. We know we're greater than 11.3, but we're not to 11.4. So you estimate how far between the 3 and the 4 you are. So you would read that to, I would say, maybe 11.36. The last digit is an estimate, but it's 2 places past the decimal. So all burette volumes should be read to 2 places past the decimal. All right. So 2 places past the decimal, read to the tenths, estimate to the hundredths. Last thing about working with a burette is that you should record the volume you see. You do not subtract the volumes from 50. Alright, so that means is when you start out, if you filled it up exactly, it's 0, 0, 0.00 if you're exactly on the line. Let's look at this thing one more time. Notice it's 0 at the top. So if you record this all the way to the top and your bottom of your meniscus is right on that line, then that's 0. It's not 50 mils when it's filled up, it's 0 when it's filled up. Okay, so one more time. Stopcock is open when it's parallel to the tube and closed when it's perpendicular. Always read the bottom of the meniscus. Record every burette volume to 2 places past the decimal. Read to the tenths, estimate to the hundredths, and last, record the volume you see. And that concludes this lab lecture.